here's an example problem that involves a Thevenin, no, I can't get this out right. Here's an example problem that involves a dependent source. So we have to use that test voltage or test current to find our R Thevenin / R Norton. All right, so let's first find our V Thevenin, because that one's actually not too bad. So the load has already been removed. We don't know what's over here. We don't care. But our V open circuit, our V Thevenin, is right there, which means also right there. If we want to go ahead, we can label this node Vx, and I'm going to use nodal to find V Thevenin. So I have V Thevenin minus 0 over 4. Again, I'll write down we're using nodal. Plus V Thevenin minus Vx over 3 equals 0. I have Vx minus 6. Hopefully you're getting pretty good at that now. Over 5. I have 1.5 Ix entering. And I have Vx minus V Thevenin over 3. So I need to do something with this Ix, because right now I have 2 equations and 3 unknowns. That doesn't work. Well, Ix is right here. So Ix can be replaced with Vx minus V Thevenin over 3. So if I make that substitution and I do all that algebra, I get a V Thevenin of 5.33 volts and a Vx of 9.33 volts. Now you could have done this with a mesh if you wanted to. You'd get a super mesh here, but you'd still have 2 equations and 2 unknowns. So either way, whatever works, but you'll get the same answer. But now we need to find R Thevenin. Okay, so to find R Thevenin, we want to deactivate our independent sources. This is still 1.5 Ix. We've done nothing to that. 3 ohms. Ix still defined here. We didn't change that. So I can get this marker to start working a little better. We have 4 ohms. And now we have to choose. You add a test voltage or a test current. I'm going to go ahead and add a test voltage. Now why do we need to do that? Just think about it for a second. If that doesn't exist, well, for one, we can't find an equivalent resistance when this is in there. What do you do with it? It's not in series, not in parallel, it's not even a resistance. And for 2, this is a dependent source, meaning it depends on something else in the circuit. So without an independent source somewhere, there's nothing happening, right? It's like having a watch without a battery. It's not going to do anything. So we'll add this test voltage. We're going to go ahead and let it equal 1 volt. And we need to find that IT value. So since we did nodal over there, let's go ahead and do mesh over here. I'll call that let's keep it consistent here, I1. Convenient thing for this would be Ix, right? Because it is Ix. What about this one? Well, it's the opposite of IT. You know what? I'm afraid I'm going to confuse you if I do that. Let's just go back to calling this I2 and calling this I3. And then right here, let's go ahead and recognize that I2 is equal to Ix, and I3 is equal, your sirens, I don't know if you can hear that, to minus IT. All right, so using mesh, what do we have? I didn't write this 5 here. There we go. I have 5I1. Oh, don't know what to do. Must have a super mesh, right? So we have a super mesh between I1 and I2. So that completes my I1. Go over here. I have 3I2 plus 4, I2 minus I3 equal to 0. So that's my first equation. I get my other equation looking at this node. I have I1 and IX leaving, I2 entering. Again, IX is I2, so I can replace that with I2. So there you go. There's my second equation. And over here in my I3 mesh, I have 4 times I3 minus I2 plus 1 equals 0. So I solve for I1, I2, I3, and the one I really am interested in is the I3, right? So I3 turns out to be negative 2.25 amps. I3 is equal to negative IT, so that means that my IT is positive 2.25 amps. That's a lot of work. So now my R Thevenin is equal to R equals